Good morning, Simon and fellow researchers. We're Group 9 of ECMT 3150 from the University of Sydney. The topic of research we propose is on the effect of Australian house prices on consumption expenditure prior and during COVID-19. We believe this topic is relevant because by comparing the normalized effect of house prices on consumption against the contemporary shock of COVID, it provides an insightful understanding on the magnitude of impact house prices have on consumption during the current economic and social landscape. This finding will be meaningful for policymakers, especially for the Reserve Bank of Australia, on whether maintaining Australia's low cash rate environment at 0.1% is effective in boosting household consumption and achieving economic growth. Now let's look at the in-depth effect of COVID-19 and why our research proposal is relevant in the current Australian landscape. Since the start of the COVID-19 pandemic, the RBA maintains cash rate at 0.25% from 20th of March this year to the November 2nd. Before announcing another unprecedented cut of 15 basis points on November 3, 2020. This downward trend has started since the global financial crisis in 2008, but in recent years, with the cash rate almost close to zero, the monetary policy is on the threat of becoming ineffective. This current monetary policy stance should theoretically boost consumption expenditure as deposit rates are almost close to zero and lending rates for the average Australians continue to drop. However, the current -7% drop in GDP in the June quarter says otherwise. The urgent debate now for academic researchers is to determine whether maintaining Australia's low cash rate environment and perhaps dropping the cash rate further is effective in boosting household consumption when the trade-off may be losing Australia's monetary instrument completely. In our proposal, Australian house prices are chosen as an explanatory variable for consumption, because we recognize housing as the dominant component of wealth in a typical Australian household, accounting for 39% of total household wealth. Numerous studies that were published before COVID-19 crisis have also reviewed a positive correlated pro-cyclical trend of house prices on household consumption expenditures. And Tasio in 2011 found a positive correlation on household consumption expenditures between house pricing. Nomnak and Kochler has concluded that a $1 increase on housing wealth will bring a 3-cent significant increase on ordinary consumption expenditures. Wheeler and Yates in 2017 have also summarized transitioning mechanism of housing wealth effects on household consumption. Although empirical results have suggested that housing prices can be a strong indicator that affects the household consumption expenditures. Therefore, by analyzing the comparative results of Australian house prices and consumption expenditure prior and during COVID-19, we believe that this will provide new insights to macro policy makers.
Moving on to data description, we use Consumer Sentiment Index, which measures changes in the level of consumers' confidence in economic activity as a proxy variable, since it has a significantly positive correlation with consumption expenditure as suggested in many studies. Also, Consumer Sentiment Index is in monthly frequency, whereas consumption expenditure is only available quarterly. Data needs to be in a higher frequency in order to acquire more observations and hence a larger sample size for the during COVID-19 period. The Consumer Sentiment Index data has already been seasonally adjusted, so there should be no seasonality. Home Value Index is used instead of residential house prices because, again, it is in a much higher data frequency. This Home Value Index provides daily movements in the value of combined dwellings across the 5 major capital cities in Australian housing markets: Sydney, Melbourne, Brisbane, Adelaide, and Perth. The observations of data start from November 2019 to October 2020 in our regression, in which November 2019 to February 2020 is the before COVID-19 period, and March to October 2020 is the during COVID-19 period. The Westpac Melbourne Institute Consumer Sentiment Index is collected from the monthly activity indicators H3 statistical table published by the RBA. The original data is in monthly frequency, starting from January 2010 to October 2020. The Home Value Index is collected as a back series over last 365 days on the CoreLogic website on the 29th of October and the 1st of November 2020 to obtain datasets starting from the 31st of October 2019 to the 1st of November 2020.
Moving on to data cleaning, we first cleaned the Consumption Sentiment and House Value Index datasets separately. This process includes converting dates into proper date format in R, as well as converting character-stored variables into numeric values to conduct numerical analysis, mainly to run a model. The house index dataset contains house value index for 5 Australian cities, and we included them all in our model as we needed more observations for data normalization and to make a valid conclusion from the analysis. This is because we only have a limited amount of data available during COVID, as it has only been recent since the pandemic has started, so we decided to include all 5 cities as our independent variables. After cleaning these two datasets separately, we combined everything into one and reshaped the data so the 5 cities were now considered as variables, not as column names. Lastly, we created a COVID dummy variable that takes a value of 0 before COVID and 1 during COVID, assuming COVID in Australia has started in March.
Based on a series of features and evidence that are derived from the original data, we decided to use a fixed effects model with the assistance of least squares dummy variables for the estimation. We will now introduce the logical path of our model selection. We initially noticed that the data we've used for estimating the explanatory variables is panel data, which can be clearly confirmed by its natural features. 5 cross-sections represented by 5 different cities across a series of time, which is 12 months within a year. Therefore, for the panel data, original measures such as a simple regression and a Riemann model will not fit the actual situation. A specific model for panel data based on pooled regression measures is what we should at least seek for. Thus, we headed into deciding a particular model among different choices. We've done this step by analyzing our data in 2 dimensions, qualitative aspect and quantitative aspect. We found several qualitative features of the data that are useful for deciding our model. Firstly, the data we used is not a sample, but a population. It has not been randomly chosen but collected arbitrarily and classified into specific groups, which makes it easier for us to control individual effects. Secondly, the research has focused on 5 capital cities in Australia, which to a large extent implies the similarly homogeneous behaviors of consumption among the consumers that we're studying on. The third one, also the one that can be derived from the second feature, is that there is also a need to control the effects brought by endogenous factors, which in our case is the differences among cities. As we found that there are not individual correlated effects caused by factors other than the global, homogeneous, and roughly unchangeable regressor on the health index. Thus, it is reasonable for us to expect a fixed effect model to be applied to our data. After reasoning this hypothesis, it's time for us to actually run the fixed effects model to further test them in quantitative method. In our estimation results, the p-value of the f-test for the individual effects lies within the significance level, which not only implies that the coefficients of our model are globally significant, but also indicates that fixed effects are non-zero and cannot be ignored. We've also run another random effect model and compare them by conducting a whole-span test. The p-value we got indicates a significant result at 5% level 2, which also tells us that fixed effects model is more consistent than the random effects model. Summarizing, in our case, a fixed effects model is exactly what we're looking for. So here's how our final model looks like, and I would provide general explanations for each of the components of this model. Consumer sentiment is our dependent variable, consumer sentiment, which is represented by West Bank's consumer indexes that are published monthly. Next one is beta 1, multiplied by the original data house price IT. And this represents the global coefficient of house prices effects on consumptions across 5 cities. We can also notice that there are 5 dummy variables, CID, MELB, BRIB, AD, and POST, which represent different city groups. We chose to get rid of the intercept term in need for creating a base group and apply the model with 5 dummies to avoid dummy variable trap caused by multicollinearity. And don't forget the muse here in front of the dummies, which are coefficients of them. And we got COVID here, which is another dummy variable that stands for the shock brought by COVID-19 crisis, and we have a gamma here as the coefficient. The last one, UIT, needless to say, is the error term.
The fixed effects model has the following assumptions. Firstly, error is uncorrelated with observations for the variable x for the NTI over time. If this assumption is violated, we'll face omitted variable bias. Secondly, variables are ID across time and are selected by simple random sampling. Thirdly, large outliers are unlikely, and lastly, no perfect multicollinearity. It is difficult to check the model assumptions for the fixed effects model. However, to ensure a strict IID sequence, a 5% significance level is used for hypothesis testing and the Dijon box test to test for white noise. The result sees that the error is a white noise process, but this only means our residuals are independent. It does not imply an IID sequence, therefore we tested for homoscedasticity with a BP test. The result shows that the residuals are homoscedastic as the p-value is greater than 5% significance level, reaching the conclusion that errors do follow a strict IID sequence. No multicollinearity is also satisfied because no issues were detected in R. potential omitted variable bias that may exist in the model can violate the zero conditional mean assumption, but from the Hofmann test, we can see that the p-value indicates a significance result at 5% level.
Before we move on to further model estimation and analysis, we need to check if there is a unit root in the model residuals. If there is a unit root in the residuals, it indicates that our data is not stationary, hence the model would be inaccurate and biased. To detect the presence of unit root, we conducted the augmented Dickey-Fuller test on the residuals of the OLS model. The null hypothesis of the ADF test is that a unit root is present, and hence time series is not stationary, and the alternative hypothesis proposes that our model is stationary with no presence of unit root. Our result reveals that there is enough statistical evidence to reject the null hypothesis, as the p-value was smaller than 0.01 and hence statistically significant at 5% level. Therefore, we conclude that our data is stationary. Another feature we need to test for is autocorrelation in the residuals. To test for autocorrelations, we need to run a linear regression on time t error against the time t-1 error. The null hypothesis states that there is no autocorrelation in the residuals, and the alternative states that there is autocorrelation in the residuals. From running the test regression, the coefficient estimate of residual -1 is 0.2588, and the p-value is 0.04, which is statistically significant at the 5% level. Hence, we reject the null hypothesis and conclude that there is autocorrelation in our residuals. This is not the desired result, as having autocorrelation means that our model is inaccurate and may suffer from serial correlation. To solve this issue, we can use heteroscedasticity and autocorrelation consistent standard errors that was developed by Newey and West. This issue will be covered in depth in our final report.
After checking whether the assumptions of our candidate model hold and conducting exploratory data analysis, we can now move on to model estimation. Firstly, we converted the combined dataset into panel data indexing over dates and cities. We estimated the fixed effect model by running a regression using variables from the panel data. You might find that a -1, which is in green, is added in the regression. This is to get rid of the intercept term in R and hence avoid dummy variable trap as Yihui mentioned. More explanations on this will be on the next slide. So, to see whether we should include the -1 in our model or not, we made a comparison between model 1, which is without the -1, and model 2, which is with the -1, as shown in this table. Model 1 has an intercept, whereas model 2 does not, and comparing outputs of two models, we found that the intercept estimate of model 1 and factor city seed coefficient estimate of model 2 both measure the individual fixed effect of home value index in Sydney on consumer sentiment. This leads us to the contrast between the estimated coefficients of dummy variables for cities other than Sydney in the two models. In model 1, the estimated coefficient of, for example, factor city measures the incremental difference in fixed effect between the base city, Sydney, and Melbourne. On the other hand, it measures the individual fixed effect of Melbourne in model 2. It is also worth noting that model 1 has a lower adjusted R-squared of 0.07255 and overall high p-value, whereas model 2 has a higher adjusted R-squared of 0.9937 and low p-value, indicating statistical significance at a 5% level. In conclusion, we decided to use model 2, which is consistent to the equation on model description slide after such comparison.
Here are the results we got from running the fixed effect model. From the result, we can find that the coefficient of city factors are positive and significant with the respectively small p-values, demonstrating that house prices has a positive relationship with consumer sentiment. This also can be justified by high value of F statistic and indicates a global significance, and interpret that increase in $1 of house price will hence increase consumer sentiment value that may relate to the wealth effect. However, there are still limitations in our regression. The first one would be the concern of data selection. Consumer sentiment we chose was forecasting consumer confidence for future expenditure, so there might be a time mismatch. Furthermore, the small sample size is also a problem of the estimation, which affects the reliability of our data and may lead to bias. So some important observations are not included in the data. To sum up, our presentation covered the preliminary result we obtained from the fixed effect model regression in order to investigate the effect of house prices on consumer expenditure. The investigation is mainly extended to two parts. The first part would be the data section. We first chose consumer sentiment and house values of 5 cities as process of consumer spending and house prices. In order to check whether there is union root in our data, we have run an ADF test to prove that our data is independent of the time at which the series we observe. However, an autocorrelation issue exists within our data, and we try to use New West variance estimation to solve this problem. The second part of the presentation is about model estimation. We first state 4 assumptions such that the OLS estimators are unbiased and normally distributed. Considering some empirical evidence, we chose a fixed effect model by comparing it with a random effect model, where the fixed effect model contains a more consistent estimation. After that, we started to run the regression and find that house value positively and significantly affect consumer sentiment after we adjust the estimation by adding -1 to avoid the dummy traps. According to the result, we can interpret that house owners feel they are wealthier than before and become more confident and willing to spend more in the future with the increase in house prices. Lastly, we discussed the 2 factors that may affect the accuracy of our model, which are the concern of data selection and the small sample size. That's the end of our presentation. Thank you for listening.